Okay, so let's go over these review board questions. Make sure you try them on your own before you see me go through them. So which of the following statements about coefficient of static friction and kinetic friction are correct? Both static and kinetic are proportionality constants and have the same value. No, they don't have the same value. For the same pair of surfaces, static is usually smaller than kinetic. No, kinetic is smaller than static. Both US and UK depend on if the surface is wet or dry. Yeah, right? If things are wet, they're usually slipperier. So that looks okay. And then static and kinetic depend on the surface area. No, the formula doesn't say anything about the surface area. It doesn't actually depend on the surface area. So yeah, if things are wet, they're going to be slipperier. So C is the best answer for that one. 2, 30 kilogram toboggan made of birch wood is facing downhill on a well-packed snowy slope. The toboggan just begins to slide when the applied force of 124 newtons is applied. What is the coefficient of static friction for the birch toboggan? Okay, so it just begins to slide, hasn't really slid yet, but just begins to slide. That's the key to doing this question. So this is your birch toboggan. Very important, the type of wood, 30 kilograms. Your force of gravity is just going to be Fg equals mg. So we have to go 30 times 9.81. And we get that to be 294.3 newtons. So 30 times 9.81. So that gives us our force normal, which is 294.3 newtons as well. We said that there's an applied force of 124 newtons, and it just begins to slide, which means that it hasn't slid yet. The force of friction is going to be the same. So force of friction equals mu static Fn. Throw Fn under here, so it's going to be 124 newtons divided by 294.3 newtons. And we end up getting 0.421 as our coefficient of friction. So it looks like A is the correct answer. A person applies a force of 102 newtons forward to pull a cross-country skier on waxed hickory skis. Wood is very important in these, along horizontal wet snow at a constant velocity. So constant velocity is kinetic friction is moving. If the coefficient of kinetic friction for the waxed skis is 0.14, what is the mass of the skier? Okay, so again, we'll start this with a free body diagram. That's how you should do all these coefficient of friction questions. So we have our skier like that, just a nice simple picture. And we draw our free body diagram. Everything always equals each other to start off. We have the force applied, force of friction, and it said that person applies 102 newtons of force. So we know if it's a constant speed that our force of friction is 102 newtons as well. Yeah, that's all that we know for right now. So we can go force of friction equals mu Fn, and this is kinetic, and we can find out our force normal. So if we just go 102 newtons divided by 0.14, which was given to us in the question, we end up getting 728.57. So this is 728.57. and this is 728.57. So we also know that Fg equals mg, and if we divide our force of gravity by g, so divide this by 9.81, we can find our mass. So if we divide it by 9.81, we end up getting 74.3 kilograms, and that's what our mass would be, which is D as the correct answer. So 74 kilograms. The gravitational mass and weight of a solar panel are measured on Earth and then on the moon. How will the values of the mass and weight for the solar panel compare at the two locations? So the mass is going to be the same for both, but the weight will differ. So the mass on the moon will be less? No. Both masses and weight will be less? No. Both mass and weight will be the same? No. The mass on the moon will be the same? Good. But the weight on the moon would be less. So D is the correct answer. Okay, so let's do some graphing constant speeds. So normally in class, I get someone to move out these motions, but obviously we're not in class and that's kind of hard to film. So what I'm going to use is this moving man simulation here. So I can just make him move and we can graph out what he does. So for this first one, I'm just going to give him a velocity of 2 meters per second and push play there. And we can play that back. That motion, we can graph it out. I'm just going to slow it down to make it a little bit easier. So at 1 second, it looks to be about the 2 meter mark. So, oops, we'll just time it out for every second. So we have 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. We should get the point. So 2 meters at 1 second. At 2 seconds, it's at 4. At 3 seconds, we're at 6. And you'll start to see the idea behind this right away. The trend, 4 seconds, he's at 8 meters. And at 5 seconds, he's at 10 meters. Okay, so if we graph this out, we want to put time down here in seconds, and then distance here in meters. And then we're going to do D versus T graph. And if we want to fit 5 seconds in there, we just have to go 1, 2, 3, 4, 5. And then distance, we're just going to go up by 1. So we don't need to mark every one. So we'll do it like that. And if we graph this out, 2 meters at 1 second, 4 meters at 2 seconds, 6 meters at 3 seconds, 4 is at 8, and 10 is at 5. So I can draw a terrible line of best fit with no ruler like that. Actually, that's pretty good. Oh, I can draw my little error bars around there, although there's not that much error because we have a simulation here. And you can see it doesn't go through the origin. That's okay. If it does, if yours goes through the origin, which it probably will, that's fine as well. Just don't force it to go through that origin. Okay, so we can find the slope of the graph, and that can tell us a lot of information. So to calculate slope, we use slope equals change in y over change in x, and we can use the units of our slope to tell us what we're finding. So we're going to find the slope of the graph we made. That's what we're going to do. Okay, so to find our slope, we always need a formula when doing it. And then y2. We want to use points that are easy to estimate. So let me change my color here. And we will use, this one looks close enough. And then, not really any points that are easy to estimate. So I'll just use this one right here. And this will be my point 1. This will be my point 2. So y2 is 8 and y1 is 0. And we should put our units in there. Meters and meters, and then we're at 4 seconds here, and then here I'd say, so this is half, I'd say about 0.2 seconds. Do that, and then if we calculate that, we just go 8 minus 0 divided by 4 minus 0.2. And we get about 2.1 meters per second. Okay, probably with a ruler we'd get right on 2 meters per second, and we can see we have meters up top, seconds down below, so we get units of meters per second. So our slope determines our speed. Okay, so now what we're going to do is we're going to do the same graph, but we're going to have the motion man moving backwards, and then we'll have him move slower, and then we'll have him stop to see what all those look like. So let's go back. That's what these other graphs here are for. I'm going to switch my color, and actually let's switch to blue, and we'll make our moving man do something else. So we'll clear this. We'll start him right at 10, and we'll make him go backwards. So to make him go backwards, we just need a negative speed. So we'll make him go negative 2 meters per second backwards. We'll push play. And then we'll do it like that. So we'll do our playback. At 1 second, he's at 8. 2 seconds, he's at 6. 3 seconds, he's at 4. 4 seconds, he's at 2. And at 5 seconds, he's at 0. So if we plug all that in, so 1, 2, 3, 4, 5. At 1 second, he's at 8 meters. Oops, that's a bad 8. At 2 seconds, he's at 6. 3 seconds, he's at 4. 4 seconds, he's at 2. And then 5 seconds, he's at 0. So if we graph that out, we have 5 and 0. We have 4 and 2. We have 3 and 4. We have 2 and 6. And then we have 1 and 8, like that. So we try, oops, those are terrible error bars in there. But we'll do our little circles, and we can see, oops, let's try that again. There we go. That's our line of best fit. Again, use a ruler when doing it yourself, but you can see that we end up getting a negative slope. So if we calculated this slope, which we could, we would just get negative 2 meters per second. So whenever they're moving backwards, it's a negative slope. Okay. And then if we get our moving man to move slower, so instead of moving at 1 meter per second, actually let's clear all this. Instead of moving at 2 meters per second, I'll make him move at 1 meter per second. So we'll go for 5 seconds. There we go. And then we'll play that back. So at 1 second, we're at 1 meter. 2 seconds, we're at 2 meters. 3 seconds, we're at 3 meters. 4 seconds, we're at 4 meters. 5 seconds, we're at 5 meters. So we can fill that in on our graph. I'll use a different color. So we're still going 1, 2, 3, 4, 5. But it's just 1, 2, 3, 4, 5. So if we graph that out, 1 second, we're at 1 meter. 2 seconds, we're at 2 meters. 3 seconds, we're at 3 meters. 4 seconds, we're at 4 meters. 5 seconds, we're at 5 meters. And we draw in our line of best fit like that. You can see the difference is that we're shallower. So we have a shallower slope, less steep of slope. And if we've calculated this slope, it would be 1 meter per second. Okay, and then the last one, we're just going to make him stop. So I'll stick him right here at 4. We'll clear that. And, no, it's already running. And he stopped. And we play that back. Well, 1 second he's at 4. 2 seconds he's at 4. 3 seconds he's at 4. 4 seconds he's at 4. 5 seconds he's at 4. So if we graph that out, right, switch up my color again. Let's do yellow. So we have 1, oops, that's a terrible color, I can't even see that. Let's use red. 1, 2, 3, 4, 5. Well, all of them, he's at 4. So what we're going to see is just straight across like that. So you can see it's a flat line when our moving man is stopped. And if we calculated this slope, a flat line is a slope of 0. So we get 0, they're moving 0 meters per second. That makes sense. So that's kind of what graphing is like. We start off nice and easy. It does get harder than that. Okay, so slope determines speed. Our y value is going to determine something else. Let me switch to black again. Your y value will tell you how far your object has moved in a certain period of time, right? So what we can do is we can take these certain times. So if I want to know, well, at 10 seconds, how far has my person gone? Well, I just have to go here to my y value. Oh, they've moved 1.5 kilometers. If I want to know how far they've gone at 28 seconds, I just go here, and then I go to here, and I would say that's 3.4 kilometers, right, at 40 seconds. I find my y value, and my y value is right on 4, so they've moved 4 kilometers. So your y value can tell you how far your object has moved, whatever that object is. So let's do a little summary. So slope represents speed or velocity, depending if direction matters to us. Our y value represents our distance or our displacement, depending on if direction matters. And I'll put a little star by that because there's certain situations where that might not quite work. Moving forwards is a positive slope. Moving backwards is a negative slope. And stopped is a 0 slope. Okay, if I'm moving faster or moving slower, well, faster is going to be steeper, and then slower is going to be shallower. That's how we can spot what each situation looks like. Okay, so let's do an example. These are questions you'll see in your workbook. These are questions that you'll see on the test. So find the velocity from 0 to 10 seconds. So if we want velocity, we want to find slope. If I give you a graph, find velocity with slope. So I'm going to choose 2 points here. So the two most obvious points are the start and the finish. And I'm going to find the slope. This is 0.2, this is 0.1, and I'll go y2 minus y1 over x2 minus x1. Look at that perfectly straight line. I wish I could do that with my slope. So y2 is 60. We'll put in the units of meters. y1 is 0 meters. x2 is 10 seconds. Minus 0 seconds, and I can do that in my head. So I'd say that's 6.0, probably 2 sig digs with this. Meters per second would be my answer. But I got to be careful because it's asking for velocity. So this is a positive answer, which means that I'm moving forwards. And if I leave out that forwards, well, technically it's not correct then because I'm finding speed, not velocity. So make sure you add that on there. So people usually do good with this first one, but when I throw in the second one, that's when they start doing weird stuff. So what is the velocity at 39 seconds? Well, what a lot of students will do is they'll find 39 seconds, and they'll be like, okay, there's 39 seconds, and then for some reason they find y value. You shouldn't do that. Velocity is slope. So find slope. Never use v equals d over t on a graph because it doesn't work most of the time. Very few times it does work. So find the slope, right? During this whole section here, the speed doesn't change. So just use the start and the finish. So this is 0.1, and this is 0.2. We're going to use the same formula. So my y value 2, I can tell is exactly on minus 40 meters. Okay. 1 is always the first one, 2 is always the second one along the line. y1 is 60 meters. x2 is 40 seconds. And then x1 is right at 15 seconds. Okay, so find slope if I'm asking for velocity or speed. So then what I can do is on top, it's negative 40 minus 60. And then on the bottom, it's 40 minus 15. and I end up getting, probably good to 2 sig digs, negative 4.0 meters per second. And because it's negative, because it's asking for velocity, I would add backwards. So that's going to be my answer for that second one. Okay, what is the object's displacement in 20 seconds? Well, that's easy. But what is the distance traveled at 20 seconds as well? So that, how do we do that? How is that different? So I'm just going to erase this stuff here. So I like to, whenever it's asking for distance or displacement, I like to look at it in terms of chunks. So what I mean by that is how far does the person go in this first chunk here? Well, they start at 0, and then here my y value tells me I'm 60, so they move 60 meters in this section. Okay, this is a flat line, so they're stopped. And then here's 20 right here, here's where I'm ending. So they started at 60 is my y value, 40 is my y value there. So if I go from 60 to 40, well, they've moved 20 meters. So now we need to think, what's the difference between distance and displacement? Well, displacement is direction, distance is not. So if I'm calculating distance, I would just go 60 plus 20 meters, and I get, well, they've moved 80 meters. If I'm going for displacement, well, direction matters. This is positive, this is negative, so I need to go positive 60 meters, and I need to add that to negative 20 meters, and I end up getting positive 40 meters, and I need to add my direction, which is forwards. Okay? So if we just look at the y value on the end, well, it tells me 40. So that would tell me my displacement, but it wouldn't tell me my distance. So that's why I think it's good to just do it in chunks like that every single time, and then just add them with positives and negatives for distance and displacement. Okay. Let's do a board question. So try this on your own and see if you can do it. So pause the video. Find the total displacement of a man traveling from north to south after 6 seconds. So if you've done this already, what you'll see is that what a lot of people will do is they'll just go and they'll find the y value here, and they'll say, displacement is 20 meters forwards or 20 meters north. Actually it says north to south, so you should stick with what's given. But that's not actually correct, right? And if we do it in chunks, well, they've moved from 20 to 60, so they move 40 meters forwards. Here they move 0 meters, they're stopped. Here they move 0 meters, they're stopped. And here they move 40 meters backwards. Well, if we're finding displacement, we want positive and negative. Well, they actually start where they finish, so their displacement is 0 meters, neither north nor south. So that's why it's always good to do it in chunks, because sometimes if you just find the y value at the end, if they don't start at the beginning, well, that doesn't tell you, or if they don't start at 0, that doesn't tell you the correct answer. So always do it in chunks so then you don't make that mistake on a test. So another type of graph that we need to know how to do are velocity time graphs. And right now we're dealing with physics principle 0, where everything is moving at a constant speed. So this is what our graphs are going to look like. So what does your y value tell you about the graph? Well, what can we find at 3 seconds? So this is our line of best fit here. And at 3 seconds, well, they're 10. 10 what? Well, 10 meters per second, right? The y value tells us the velocity, so they're moving at 10 meters per second. So my y value tells me speed or velocity, right? Positive 10 meters per second, so it's forwards. Well, what does the slope tell us about this? Well, if I choose 2 points, let's choose this point here as point number 2, and this point here is point number 1. I think you'll know what my slope is, but let's just play around with it and see what it looks like. So y2 is 10 meters per second. y1 is 10 meters per second. And my time is 5 seconds, and then 0 seconds. So 10 minus 10 is 0 meters per second over 5 meters per second. So 0 divided by 5 gives me 0. oops, not meters per second, seconds. 0 meters per second over 5 seconds. So, but what are my units? Okay, meters per second, is that going to give me meters? Is that going to give me meters per second squared? An easy way to look at that is using old division rules, right? So if we do meters per second divided by seconds, or seconds over 1, same thing, well, we can just multiply, the reciprocal. So instead of going seconds over 1, we go 1 over seconds. And you can see here we have 2 seconds on the bottom and a meters on top. So we end up with meters per second squared. So this is 0 meters per second squared. And if you remember meters per second squared from anything else that you've done, that is acceleration. And right now we are not accelerating. So it makes sense that our acceleration is 0. So a flat line doesn't mean that we're stopped. It means that we're not accelerating, which is very different than the distance versus time graph. So velocity time graphs are very different than distance versus time graph. So how would I show something that's stopped? Well, remember that our y value is speed. So if I want something to be stopped, well, I would just have something going right through here, because at 1 second I'm 0, at 2 seconds I'm 0, at 3 seconds I'm 0. So it's still a flat line, but it's got to go through 0. How would I show something that's moving backwards? Well, this is positive velocity, which means forwards. So this is negative velocity, which means backwards. So if I wanted to show something that's going backwards at a constant speed, well, it'll just be a flat line at negative. It'd be below the x-axis. And how would I show something moving slower? Well, if this is 10, this is going to be 5. So I just have a flat line through here. That would be at 5 meters per second. So it's going to be closer to the x-axis. Okay. There's one more thing that we do need to know about these velocity times graphs, and that's the area under the graph. So area under the graph is finding the area from 0 on the x-axis to where your line of best fit is. And you need to know that to find the area of a rectangle, it's length times width. And then a triangle is 1/2 a times b, or base times height. And we're all pretty familiar with that because we've done that a lot in junior high. So I'll show you an example of that. So if we want to find the area under the graph, what we need to do is we find the 0, which is right here. So this is where we start at 0. And then this is our line of best fit right here. We need to find this area inside of here, all of this. So this makes a rectangle. So we need to use our rectangle formula. And our rectangle formula is length times width. And a lot of time I say x times y instead of length times width. So our x is 5 seconds. And our y is 10 meters per second. And we're multiplying those two numbers. So we get 50. But 50 what? Well, we have seconds on top and seconds on the bottom, and we're multiplying these two numbers. So we end up with 50 meters. So what this tells us, area under the graph, it'll tell us our displacement or distance. Okay, so let's do a little summary. Slope represents, which we're not going to use right now, acceleration. And y value represents speed or velocity. Okay. Area under the graph represents our distance or displacement. Moving forward, so let's draw a little graph here, let's draw a little graph here, and let's draw a little graph here. And then we'll draw one graph to sort of compare slower and faster, and I'll switch my color. So moving forwards means you're up here, which is above x-axis. Moving backwards is down here, which is below x-axis. Stopped means you're at the x, sorry for the messy writing, axis. I have to do with my mouse because I don't have a stylus or anything, so this is the best I can do. And this is not a plus, this is the x-axis. Moving faster is like this, and then moving slower is like this. So moving faster is further from x-axis, and then moving slower is closer to x-axis. Okay. So this summary chart is really useful. When you're doing the homework, have this out on your desk or wherever you're working, on your bed. And then, so when I ask you these questions, you can have this out here, and you know what each of those represents. You need to memorize this whole chart for your test. Let's do an example together here of all those different things. So find your velocity at 6 seconds. What do we do? Velocity, is your y value. So that's what we're going to do. So we're going to find our velocity at 6 seconds. So we'll go down here to 6 seconds, and we'll find our y value. So our y value looks to be 6. So my answer is 6 meters per second. But it is velocity, it is positive, so I'd have to add forwards to it. Okay. Displacement between 5 and 10 seconds. How do I do that? Displacement, area under the graph. So I just have to find the area under the graph. So I'm going to erase my line here. There we go. So we want to know between 5 and 15 seconds. So I need to go from 0 on my x-axis to my line of best fit, which is right here. So I need to find this area right here. Okay. So it's a rectangle. So it's length times width, or y times x. My x goes from 5 to 15, which is 10 seconds. And then my y goes from 0 to 6. So it's 6 meters per second. So 6 meters per second, 10 seconds gives me 60 meters. Double check displacement. So that's positive 60 meters, which means forwards. So 60 meters forwards would be my answer. Total distance traveled. So we need to find our areas for everything, right? So we already found this one here. So we need to find from 0 to our line of best fit here. We need to find this area in here. So my base is 5. My height is 1, 2, 3. So 5 times 3 gives me 15 meters. This, what's going on here? Well, I'm right at 0, so this I'm stopped for. So this doesn't have an area because I'm not moving anywhere. Okay, and then for our next section, we need to do this one here. So we go from our 0 line to our line of best fit, and we find this area here. So this area has a base of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, just double checking that. Yeah, so 5 seconds, and then we go 5, 10, 11. So 5 times 11 will give us 55 meters in this. And then our last one, we go from our 0 line to our line of best fit, which is this area right here. So our base is 1, 2, 3, 4, 5, 6, 7, and our height is 10. So 7 times 10 is 70 meters. So we go 70 meters. So we just have to add that up for our total distance. Positive and negatives don't matter. That's why I didn't really include it. So we go 15 meters in the first one. And then we found this area was 60 meters. And then we stop for a bit. And then this one here is 55 meters. And this last one is 70 meters. So we just add them all up. Positives and negatives don't matter. So when I type that into my calculator here, I just go 15 plus 60 plus 55 plus 70, and I get 200 meters. Okay, The direction doesn't matter, so 200 meters is my answer. My total displacement, well, now I need to include positives and negatives. And how do we find positives and negatives? How do we find forwards and backwards? Well, let's take a look here. So what does moving forwards look like? Well, moving forwards is above our x-axis. Moving backwards is below our x-axis. Okay, so if we want to do that, then this is above, so this is positive. This is positive. This is stopped. This is negative because our line here is below our x-axis. And then this is positive because it's above our x-axis. You can see that these three are on top and this one's on the bottom. So when I add them up, I'm going to go positive 15 meters plus positive 60 meters plus negative 55 meters plus 70 meters, positive 70 meters. Okay, so I go back into my calculator. And if I could just go second enter, it'll type in the same thing. So the only thing that I need to change to negative is this 55. So I'm just going to insert a negative there. And I get 90 as my answer. So this is positive 90 meters forwards as my answer. For my next one, I want to find the average speed over the whole trip. Well, how did we find average speed before? Oh, well, to find our average speed is just going to be our distance total over our time total. Right? We already know our distance total. Our distance total we found to be 200 meters. And our time total, well, it looks like it ends at 30 seconds. So it ends at 30 seconds. So if I type that into my calculator, 200 divided by 30, I end up getting 1.6666. Probably good to 2 sig digs on this. So I'm going to go 6.7 meters per second. And that's all you need to do. To find average velocity, all we have to do is make these vectors. So instead of this being distance total, it's displacement total. And my displacement total is positive 90 meters. And we still do it over 30 seconds. So 90 divided by 30 is going to be 3.0 meters per second. But it's positive, so we need to include forwards. Okay, and that's how you're going to do examples. So as long as you have that summary chart when doing your homework, you can do any question. This isn't like require complex thinking. It just requires you to know your stuff.
Let's do an example.
Oops. Sorry. Okay, let's do a board question here. Board question, yeah. So I'm going to get you to find these 3 things, so see if you can find them, and that's all. So pause the video. So velocity at 45 seconds. Well, here's 45 seconds. My velocity is my y value. So velocity is -1 meter per second, and then backwards. And probably go 1.0, probably 2 sig digs, but I don't care too much about sig digs with graphs. Average speed, well, we need to find our total distance. So in this section, excuse me, so this section here, we go 0.4 meters per second, and we multiply that by our base, which is 20 seconds, right? 0.4 here. And then that's going to give me 0.4 times by, what did I say, 20? So that's going to give me 8. So this is 8 meters for the first section. And then here we're stopped. So this section has a base of 10 and a height of 1. So it looks like they moved 10 meters. 10 times 1 is 10. So my average speed is going to be 8 meters plus 10 meters divided by my total time. This is a little bit sketchy. I probably wouldn't do this on a test. It looks like it stops here at 50, and there's no line for 60. So it'd probably be 50 seconds, not 60. But I wouldn't put the 60 on in a test. So if we go 18 meters divided by 50 seconds, and I calculate that, 18 divided by 50, I get 0.36 meters per second. Okay. And then for average velocity, well, this is positive and this is negative because this is above the x-axis and this is below the x-axis. So I would go positive 8 meters plus negative 10 meters all over 50 seconds. So I'd end up getting negative 2 meters over 50 seconds. So if I calculate negative 2, oops, I'm trying to use my keyboard here and get all fancy, but that's the minus sign. So if I go negative 2 divided by 50, I end up getting 0.04 meters per second. It's negative, which means it's backwards. So my average speed is backwards. Okay, that's a board question. Oops. So this is your homework. So this is D versus and see how that goes. So because this is our last lesson before our quiz, we'll do our review board questions now. So make sure you try them on your own and then watch them after you go through them. So refer to the following motion graphs to answer the question. The graphs that show an object going uniform motion, so constant speed, are, well, we have velocity versus time graph and position, which is the same thing as distance versus time. So velocity, time, and then acceleration versus time. That's a little bit weird. Could be a constant speed. So they're going 5 meters per second the whole time. So this is good. That's going at constant speed. A distance versus time graph, we just want a steady positive slope. So this is good. This shows a slope, which means there's acceleration for velocity time. So that's not good. And then acceleration versus time, I don't really talk too much about, but they're really easy. This would be having acceleration and this would be not having acceleration. So what that means is this has an acceleration, and if you have an acceleration, you're not moving at a constant speed. So that's not good. So 2 and 3 are the correct answer. Okay, the total displacement over the 10-second period is, so we need to go from the 0 to our line of best fit. We need to break this up into 2 different rectangles. So this has a base of 4 and a height of 30. 4 times 30 is 120 meters. And this has a base of 2, 4, 6, and then a height of 10. So this is 60 meters. So total displacement, well, they're both positive. They're both above the x-axis. So that's going to be 180 meters. Okay, and this one here, the corresponding position time graph. So this we're going at constant speed, and it's above the x-axis, so this is forwards. So we have a constant speed forwards, and then this is a constant speed backwards. So on a position time, this is forwards, this is backwards, which makes C the correct answer. And then number 4, for the position time graph, an object moves east for 8 seconds, the velocity. So for a position time graph, if we want to find velocity, we have to find slope. If you try any other way, you'll get the wrong answer. So this is 2, this is 1, just use a whole line. I'll always make those lines really easy to estimate. So we go y2 minus y1 over x2 minus x1. y2 is 24 meters. y1 is 4 meters. y2 is 8 seconds minus 0 seconds. So we have 20 meters over 8 seconds. And what is 20 divided by 8? 2.5. So the only correct answer is 2.5 meters per second. And once a 2-digit answer, this is 2 digits. And that's it.